So the next topic in Chapter 2 covers the basics of vector operations. So we're going to look at more vector operations as the course goes on, but we're going to start with the basics of scaling and adding and subtracting. So first of all, what happens, or what does it even mean to scale a vector? Well, remember that vector quantities and scalar quantities are different. But if you take and multiply a vector by a scalar, all that's going to do is change its magnitude. Now, I say that with a bit of a caveat. As you can see here on the right, clearly this vector minus a is just scaled by the constant minus 1. And you would say, well, hey, its magnitude actually didn't change at all. Its direction certainly looks like it changed, but these are more edge cases. Really, when you think about scaling a vector, what you're thinking about is multiplying by a constant in order to change its magnitude. So that's what the term scalar multiplication refers to, is taking a vector and just multiplying it by a scalar. Now, if that scalar is greater than 0, that's not going to change the direction at all. If it is less than 0, or it's a negative number, the line of action that you refer to of a vector, and usually that's a term that you would associate with a force, but what line of action means is if you draw just this axis that is parallel to the vector, if you rotate it at 180 degrees along that line, that is the effect of just multiplying by a negative 1 or a negative number. And we can see that clearly in this case of minus a. It looks just like a. It has the same magnitude, but it's rotated 180 degrees along that line of action. If the absolute value of whatever you're multiplying by is bigger than 1, that's actually going to increase the magnitude. So you use the plus or minus to kind of maybe redirect it or rotate it by 180 degrees. If you multiply by a magnitude of greater than 1, it will increase the magnitude. If it's less than 1, of course, that will decrease. And you see that here in the visualization. 2 times the vector a, that's a scaling. Since 2 is absolute value bigger than 1, you make it twice as big. Here, minus 0.5, the minus effect will rotate it 180 degrees along its line of action, and multiplying by 0.5 will cut its magnitude in half. So how do you actually go about adding vectors? Well, the text actually describes 2 approaches. I'm trying to think back of when I saw this originally in my multivariable calculus class. It was a very, very long time ago. I thought we just jumped right to the triangle rule, but I remember when I took this class in statics, actually thinking that the parallelogram rule was a bit unnecessary. But we're going to go over it since it's in the text, the way that we will do that if I want to add vector A and vector B, and think about it like why it has to be this way. And the easiest way is to always just think about displacements. If I walk a meter to the right and I walk a meter up, what is my total displacement? Well, relative to the origin of that original vector, I'm going to have a displacement which is defined by a vector going from here to here. So that's actually the triangle rule that I just showed you with my hand. But what's going on with the parallelogram rule, if I want to add these, is I will place there. Now, the thing we need to be careful of, and I will undoubtedly mess it up as we talk because it's easy to swap the 2, is that all vectors have a tail and they have a tip. And the tip is where this arrowhead is on. They start at their tail and they extend to the tip. So if I want to add A and B, I take their 2 tails and I put them together. Then I draw lines which are parallel to both vectors. In this case, this would be the line that is parallel to A. This would be the line that is parallel to B. I mark that point of intersection of those 2 parallel lines. And if I draw a new vector from the common tails of both vectors to that point of intersection, that's actually what the resultant is. And we call that the parallelogram law because if basically you throw away the portions of those lines after the common point of intersection, you get a nice parallelogram where your resultant or some vector is just kind of serving as a diagonal of the parallelogram law. So if you think about the triangle rule, that's going to be a more simplistic way to add vectors. Here, rather than aligning the 2 tails of the 2 vectors at a common point, you're going to place the tail of one on the tip of another. And here they've done that. When adding A and B, we've taken the tail of B, we've put it on the tip of A. And once I have that new alignment, all that I need to do is close the triangle, and that gives me the resultant vector or sum of those 2 things. So notice that, of course, addition is commutative, so it doesn't matter whether I put the tail of B on the tip of A, or alternatively, if I put the tail of A on the tip of B, in both cases, I will get the same thing. And if you look at those and you kind of put them together, you'll recognize that that's just the parallelogram that we had in the previous slide, actually taken apart from the 2. So how would you ever go about subtracting vectors? Well, remember, you're an engineer. You're always going to try to make things as simple as possible. So remember that subtraction of any type of mathematical quantity is just adding the opposite. So if you can just scale the second quantity by negative 1 that you're trying to subtract. And of course, we know how to do that. We know that scaling by negative 1 doesn't affect the magnitude. It just rotates the vector 180 degrees along its line of action. So if I want to subtract B from A, one way that I can do that is just take B, leave its magnitude alone, rotate it 180 degrees, and if I'm following the triangle rule, I'll place the tail of minus B at the tip of A, and I'll just close my triangle. And of course, you could do it via the parallelogram law as well. What does it mean? And we're going to look at this in a lot more detail, of course, over the rest of the semester to actually resolve forces into components. What that means is I can always, because of that underlying definition that I have for the triangle rule, I can take any vector in a two-dimensional space, and I can drop a perpendicular from the tip of that vector to some other axis. And naturally, what that will allow me to do is to find two new axes for which I can write my original vector as the sum of two other vectors. Now, it doesn't necessarily have to be, and I know where you all are thinking with this, oh, that's like decomposing into x and y coordinates. But notice here, this u and v axis aren't orthogonal to one another. In fact, they clearly are not. The thing that they share in common is they're both aligned along particular members of this assembly. So when we get to the analysis of assemblies or trusses later on in the course, this is a technique we will use very often. So just from a physical point of view, it's often beneficial to decompose a force into components which are aligned along particular members of the body, particularly when those members are load-bearing in tension or compression. So just for a quick example of this, just a very quick example, we're going to do more on the homework. If I have two vectors, F1 and F2, and I have this vector called R, the question is, what would be this vector R? Well, clearly it's not just the sum of F1 and F2, because remember, kind of just looking at the triangle as we have it here, if we wanted to use the triangle rule, we would need the tail of one to be aligned at the tip of the other. But let me ask you a question. What would happen if I scaled F1 by -1? Well, its magnitude would be the same, but all that would really happen is this its tip would move over to here and its tail would come here, right? Because you would just rotate 180 degrees along the line of action. So if you look at this vector F1, if the arrowhead were moved over here, then you would have what's known as a tip to tail arrangement. That would be this vector plus F2. So what would that vector be? It wouldn't be F1, it would be minus F1. So in this case, what we're looking at is minus F1 plus F2. That gives us the tip to tail version of the triangle rule. So that's why this answer was correct when it was entered into my lab, which all of you will get to do very soon whenever the bookstore gives us this access.